In this video, we're just taking a quick look at a characteristic X-ray that's produced by tungsten when it's bombarded with energetic electrons. So we're not getting into the details of X-ray production here, but this thing is called the K-beta transition. It's a transition from the n=3 to n=1 energy state. So these inner orbitals of the very large tungsten atom. And when we smash energetic electrons into a tungsten target, occasionally one of these electrons will be knocked out of place, and we'll end up with a transition from the n=3 to n=1 energy level, producing an X-ray with a characteristic energy of 67.2 kiloelectron volts. Just a quick reminder before we actually answer the question. The X-ray spectrum produced by this target will look something like this, and the vast majority of that is bremsstrahlung radiation. That's when electrons slow down. So when electrons slow down, the missing energy has to go somewhere, and that is shed as X-ray photons with a continuous spectrum. On top of that, and this is a plot of intensity versus wavelength, you're going to see several spikes in intensity, and these are due to these characteristic transitions between energy levels in the particular metal that we're using for the X-ray production. So this K-beta transition is just one of these spikes, and I'm trying to get the wavelength of it based on its energy. So this is a very familiar calculation. It's just E=hf. You replace F with C over lambda, and now I solve for lambda, and I get Hc over the energy, and then it's very convenient to put Hc into units of eV nanometers, and it's about 1240. If you want to be a little more precise, you could use 1242, and my energy needs to be converted to eV, so that's 67,200 eV. eV cancels, and I get a wavelength of 1240 over 67,200, which comes out to 0.0185 nanometers. So remember, visible photons are on the order of hundreds of nanometers. The wavelengths of these X-rays are very short in comparison to visible photons, and they carry enough energy to ionize atoms and molecules, which is why this is called ionizing radiation. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.